So, today we're going to be talking about exponential growth and decay. We're starting a unit on the exponential function, and we did talk about exponential functions in the very first unit when we were doing sequences and series. We said that the geometric sequence was an exponential function, and so we are going to be getting to know it a little bit better today. We want to talk about the models as far as application problems, things that we can model in real life using an exponential function. We also want to talk about the graph and what are the pieces of the graph and what does it look like. So this is what we're going to be talking about tonight. So let's take a look at, just for a moment, what is the exponential function? What does everything stand for? What can we use it for? What are the pieces, so to speak, of the exponential function? So f of x is equal to ca to the x power. This is the exponential function. So for the exponential function, notice that x, the variable, is in the exponent. C and a are both going to be numbers. C and a are numbers. Okay. So x is the only variable in this problem, and it is in the exponent, thus the name exponential. Growth and decay are because there's two types of exponential models. Growth is when something is growing, getting bigger, and if you think back to our geometric sequences, anytime r was bigger than 1, the numbers in our list kept getting bigger and bigger and bigger and bigger, and anytime that r was equal to a number between 0 and 1, like a fraction or a decimal, all the numbers in our sequence were getting smaller and smaller and smaller. And so that's where that comes from. If the numbers are getting bigger, it's growth. If the numbers are getting smaller, it's decay. And so these are the parts of our exponential growth and decay model. We can use these to solve a lot of real-world applications. These are used a lot to model populations in bacteria, animals, people. They're used a lot to model money, investments, percentage, anytime you have percentage growth. So interest in a bank account and stuff like that, that's always going to be some kind of exponential. We also see them pop up specifically with things like half-life in chemistry, with the decay of things like that. So it's a very commonly used function. So as far as what does everything mean in a word problem, C, this number up front, it is a number that is being multiplied. You know, A is what is being taken to the x power. This is the exponent. C is being multiplied after you have taken that number to the exponent. And it is always going to be some kind of starting value. So that kind of depends on the problem. If the problem is I'm putting money into the bank, then that's how much money I started with in the bank. If it's a half-life problem, well then how much of that compound did I begin with, before it started halving itself? If we're talking about population, what was the population the first year, the starting population, and then as far as what is it going to be in the future, that would be something else. But what year are we starting in? This is our starting value. So C is always going to be your starting value. A is what we call our growth factor. Could also be a decay factor, but it's our growth factor. And so it's like how much is it growing by or how much is it shrinking by. It's our growth factor. The growth factor is actually made up of a different number. The growth factor is always 1 plus a percentage if it is a growth problem, if it is gaining value, so whatever the percentage that we're growing by each day, each year, whatever the time period happens to be. It's going to be 1 plus that. Do make sure that we always change percentages to decimals. 25% would be 0.25, so forth and so on. And then we do 1 minus a percentage if it's a decay problem, if it's shrinking, if it's losing value. So this number should always be, some number between 0 and 1 or some number bigger than 1. Okay? That's the growth factor. And that's the number that is actually being taken to a power. It's the base, all right? And then x in the problem is always going to be our time component, all right? X stands for time. We did say that time is one of those universal independent variables. Time doesn't really depend on anything else. Time, however, can be a lot of different things. It can be years. it can be hours, it can be minutes. It just depends on the problem, so you do want to make sure you're reading your problems carefully to make sure that your time is the right time frame. When we do a problem, you could be given many different types of problems with this lovely little model. For example, if I buy a car for $12,850. It depreciates at a rate of 23% per year. How much is it worth in 3 years? So I bought a car for $12,850. And if you don't know this, folks, as soon as you buy a car and drive it off of the lot, it has lost value. Okay? It depreciates very quickly at the beginning, and then it kind of levels off at the end. So if I'm going to buy a car for $12,850, it depreciates at a value of 23% per year. How much should it be worth in 3 years? So we need some pieces of information from this problem. We said one of those pieces of information that we need is a starting value. So I want to know, how much did my car start being worth? Well, we're going to assume that the price we paid for it is what it was worth at the beginning. So $12,850 is going to be our starting value. Now we need to be able to find a growth factor. Growth factor, what is this number going to be? It's either going to be 1 plus or 1 minus something. Depreciates tells me that it is decaying. It is going down. So that means I want to use 1 minus a percentage, and that percentage is going to be 23%. Now we also said that you want to make sure you change percentages to a decimal, so this would be 0.23. We want to make sure we do use the decimal version of that. And then the last thing that we need is we need some kind of time frame. We got to be able to find our time frame. And since it's depreciating per year, our time frame needs to be in years, and it looks like 3 years is what we're going for here. So for my problem, I'm going to do 12,850 for my starting value times 1 minus 0.23, all to the third power. So I can go into my calculator and I can type 12,850, parentheses 1 minus 0.23, close my parentheses, all to the third power. And that tells me that this car should be worth about $5,866.45 in 3 years. Guys, do use some common sense. Our default for rounding is 2 decimal places. It's money. Money should never be rounded to anything but 2 decimal places. So you want to make sure that you're rounding to 2 decimal places, paying attention to what your answer is in, and make sure that your answer makes sense. But that's how much this car is going to be worth. So you just want to make sure you ask yourselves in every word problem, what is my starting value? What is my percentage for my growth or decay? So am I adding or am I subtracting that percentage from 1? And then what is my time frame? And this is how we use this lovely little equation. There is a version of the exponential function that is used specifically for bank accounts, and it's what we call compound interest. When you have compound interest, compounding interest is when you go to the bank, they give you an interest, so at the end of the month, they calculate your interest, they put it in your bank account. Well, then the next month, even if you didn't put any more money in your account, you had more money because of that interest. So you're earning interest now on that interest. So, the interest is compounding on top of itself. And so what you find is that when you go to get a bank account, the more often your bank compounds, the more money you make because you're earning interest on interest. And so you always want to ask, how often does your bank compound interest? Because the more often it compounds your interest, the more often it calculates your interest, the more money you make. And so you have to take that interest into account when you are doing your interest. Another thing people don't realize is that APR, you see that abbreviation a lot on advertisements, on TV, credit cards and car loans and such. APR stands for annual percentage rate. And so that is how much interest you make over an entire year. That is not how much interest you make every time they compound your interest. So if they're compounding your interest every month, you're not making that interest amount every month. They are taking that interest rate, dividing it by 12, and that's the amount of interest that you're making every month. So then when they add that all up at the end of the year, that's about the percentage that you make over the year. It's the average over the year. So what you need to realize is that for compound interest, we need to modify our formula a little bit. And so the amount of money left in an account after you're doing compounding interest is the principal. P stands for the principal, and that's what they call in the finance world the initial investment. What was the initial cost or the initial investment? If you take out a loan, that's the amount you took out the loan for. If you're investing in something, it's the amount you initially put into the investment. So your principal, it is LE, not AL, because AL is your pal. That's your principal at school. So it is principal. And then for our growth factor, it's 1 plus the percentage rate, but that gets changed a little bit because, as we said, you have to take the APR, the percentage rate, and you have to divide it by the number of times a year you compound. So this is how many times a year you compound your interest. So if it's monthly, that would be 12 times a year. If it's quarterly, that's once every 3 months, that's 4 times a year. Annually would just be once a year. Daily would be 365 times a year. So you have to take your percentage and divide it by the number of times that you're compounding each year. And then up here, instead of just being a time, because we're compounding more than once in a year, you do have to take the number of times that you compound in a year and multiply it times however many years you are doing it. So time does need to be in years. N does need to be the number of times that you compound each year. And so we're adding this compounding aspect into it. It's still growth factor to an exponent, and you still have your starting amount. That part stays the same. But we have to adjust it a little bit and make sure we take that annual percentage rate, divide it by the number of times it's compounding. And then we have to take our time and multiply it by, well, how many times each year is it compounding? That's what we want to do. So we adapt it in that way. So then anytime you see compounded interest, it'll say compounded monthly, compounded annually, compounded semi-annually, compounded biannually. When you see that, that is telling you, what do you need to divide by and what do you need to multiply by. Now, our graphs for exponential functions. Let's talk about the graphs for an exponential functions for a second. We know our graphs, we can shift them up and down, left and right, we can flip them, multiply them by stuff. So what that actually does to the equation, we have CA to the x, but we can add or subtract something up in the exponent. We can also add or subtract something outside of the exponent. So we need to keep those in mind. So, we can multiply it times something, we can add or subtract something inside of the exponent and outside of the exponent. These are all of the possible different things that you can do to change the equation. There are 3 parts to a graph for an exponential. The first one is the asymptote. So, just like last unit, we do have some asymptotes to deal with. It is a line that the graph is getting closer and closer and closer and closer to, but it never quite touches. All right? It is a horizontal line. It's a horizontal asymptote, and it does start at the axis as its default. Now, you can, of course, shift it up or shift it down, but it is going to start at the axis. It is always a horizontal line, and so we can't really shift it left or right. That doesn't change anything. So there's not really going to be any effect that adding inside is going to have to the asymptote. What really affects the asymptote is going to be your K value. K is really going to be what tells us where our horizontal asymptote is, because it should be at 0. So if there's no number added out here, it stays at 0. But if we add something, we shift it up. If we subtract something, we shift it down. So K is always going to tell us where our horizontal asymptote is going to be for the exponential function. The next part that you want to be able to find is your pivot point. Exponential graphs don't really have a vertex. A vertex is really where a graph turns around, stops going up and starts going down. That's what we mean by a vertex. Exponential graphs don't have a vertex. They do have a point, though, where they kind of change their direction. even if it is just a little bit, and that is the pivot point. The pivot point is where it stops being slow and it starts getting big, kind of thing. And so your pivot point starts on the y-axis, and it starts one space above the asymptote. This is its default location. All right? And what that pivot point is that's the point at which the graph kind of changes its direction. It is a critical point. Now, it can be shifted up and down. It would shift. It's always based on the asymptote. Your pivot point is always based on your asymptote. So once you have your asymptote in the right place, we need to know how far above the asymptote is the pivot point, and did it get shifted left or right any? Because that's really what we're going to be looking at. And so we could stretch it and pull it further away from the asymptote, or we could squish it and push it closer to the asymptote. And the way that we stretch and squish things vertically on the graph, if you remember, was to multiply the function by something. So C is going to be critical for the pivot point. C is going to be critical. C is going to tell us how many spaces above, how far above the asymptote is the pivot point. So is it one space above? Is it two spaces above? Is it 5 spaces above? How far above the asymptote is the pivot point? That's what C tells us. H is going to tell us whether it shifts to the right or to the left. Again, inside is always backwards. So if it's adding, we're shifting to the left. If it's subtracting, we're shifting to the right. The axis is its default location. So if nothing is added or subtracted, it stays on the axis. But that tells us whether it shifts left or right or not. You need to always graph your asymptote first, then your pivot point. The last part of the graph is the actual curve of the graph itself. And for the curve, we need to know whether it is growth or decay, because growth is getting bigger, decay is getting smaller. And the thing that's going to tell us whether it's growth or decay is going to actually be A. All right? If it is growth, A is bigger than 1. If A is bigger than 1, then this is growing, and it's going to be growth. If it is decay, then A has to be some number between 0 and 1. So some fraction between 0 and 1, or some decimal between 0 and 1, 0.5, 0.75, 2/3, those kind of things. Something between 0 and 1. So what does that look like? The pivot point is where your graph turns. If it's growth, it should be getting bigger on the right side of the pivot point, and very fast bigger. It is a curve and not a straight line, though, so make sure it is a curve. On the left-hand side of the pivot point, instead of getting bigger, it's actually leveling out. It's getting closer and closer and closer to the asymptote. Never touching it, but getting darn close. All right, so this would be a growth model. It's close, close, close to the asymptote. But when you hit the pivot point, it runs away from the asymptote as fast as it can. This would be a growth exponential model. For decay, it's going down. So on the right-hand side, it's actually getting closer and closer and closer and closer to the asymptote, never quite touching it. And then on the left-hand side of the pivot point, it's shooting up and getting as far away from the asymptote as it can. So you end up with these curves. These are the 3 things that we'll be checking for on the graphs this unit. Your asymptote to be in the right place, your pivot point to be in the right place, and your curves to be in the right place.